Hello everyone and welcome back. I'm Mr. Cobalt, and in this video we're going to go over constant volume calorimetry. And so let me start by saying what calorimetry is. Calorimetry is where you are going to be measuring the heat of a reaction using a calorimeter, right? So basically, as calorimetry says, it's the measure of the heat, the calorie, right, which is measured in joules, or or measured in calories, which is a unit of energy, which we can convert to joules if we need to convert to joules. So calorimetry, usually it involves a calorimeter. You're going to isolate a certain reaction. The reaction is our system, and what a calorimeter does is it really narrows or focuses what the surroundings are. So whenever you're given a problem that involves a calorimeter, the assumption is going to be that no heat is lost to the surroundings outside of the calorimeter. So you can pretty much limit the surroundings to the calorimeter. So any heat that's absorbed is only going to be absorbed by the calorimeter. In this case, they're going to give you a calorimeter, the specific heat of the calorimeter itself, as well. Okay, so that's a little bit about calorimetry. What do we mean by constant volume calorimetry? Well, it kind of goes back to the system surroundings relationship. So what we've seen in previous videos, or what we've gone over in previous videos, is this idea of an exchange between the system and the surroundings. It could be an exchange of heat, which is represented by Q. And so we could calculate the amount of heat exchanged between the system and the surroundings by using the mass, this equation here. So if they give us the specific heat of a substance, and they give us the mass of that substance, and they also give us the delta T, or the change in temperature, we can use the change in temperature and all this information to find the transfer of Q, the change in the amount of heat, whether it's going to the system or going to the surroundings. The other way we could measure energy change is by calculating work. And in a previous video, we talked about work being calculated or determined by the external pressure multiplied by a change in volume. And so we could use that to figure out the work. And then again, the total internal energy, the total energy of the system at the particle level is going to be the heat plus the work done. Now, in constant volume calorimetry, it kind of simplifies the whole thing, because work depends on a change in volume. So if we could change the system in such a way, or the surrounding in such a way, that the work could be eliminated, then we could force the complete energy change into heat. So we can measure the total amount of heat instead of having to deal with work. So we could simplify our equation. So if we keep the volume constant, so then the change in volume would be 0. So then that means that work would be 0 as well. So in this case, the change in energy is going to be Q at constant volume, just the number of heat. So if we could do a calorimetry keeping the volume constant, then we could figure out the heat evolved from the reaction. And so the change in energy, the complete total change in energy of the system is going to be the heat. And so the only surroundings in this case is going to be the calorimeter. So the calorimeter that we're going to be using in this type of situation is called a bomb calorimeter. And the bomb calorimeter is set up to keep the volume constant. So it's a very rigid container, and so the reaction happens in there, and so it will pick up all the heat, and we will measure the amount of heat using a thermometer. And so the way it looks is if I draw it really quickly, so you'll have a thermometer here. So that's going to measure the temperature of the water. So you have water in here, you have a container here that has our sample that's going to be burned. We're going to burn the sample, it's going to be ignited, so maybe there's a switch up here, wires are connecting to it. So you hit the switch, it's going to send electricity, it's going to burn the sample, and then you've got an electric stir here, so it's going to stir the water. So you got water inside your bomb calorimeter. So as this is heating up, it's burning our sample. This is the reaction, it's releasing heat. The heat is picked up by the water, right? So the stir is going to be mixing the water really well, so that heat is spread throughout the water evenly, so you get a good temperature change or temperature measurement. So then you can get the change in temperature from there. So you'll get the change in temperature. You'll know the specific heat of the water, right? And you'll know the mass of the water, and so on and so forth. You'll be given the mass of the sample, so you can figure out what the heat of the reaction is as well. And in addition to that, you'll be given the heat of the specific heat of the calorimeter. And so, because the calorimeter itself will also pick up some of that energy, and so you need to measure that as well. So that way we'll have all the energy, the heat that was evolved, and we can figure out what the total amount of heat evolved in the reaction was at constant volume. So in this case, the delta change, the amount of heat at constant volume, is going to be equal to the surroundings, right? So we have, this is our system, right? And then the delta E on this side, that's going to be the surroundings. So here we have Q of the surroundings is equal but opposite to Q of the reaction. So this is going to be the reaction, the heat of the reaction is equal but opposite to heat of the surroundings, which is, the surroundings is just the calorimeter, everything in the calorimeter except for the reaction. So the Q of the calorimeter is equal but opposite to Q of the reaction. So if we can calculate everything from the calorimeter, the temperature change, the heat absorbed by the bomb calorimeter itself, things like that, then if we can calculate that, then that would be equal to the heat of the reaction. So we could find the heat of the reaction in this sort of calorimetry type problem. Okay, I hope this was helpful. In the next video, I'll go over some practice problems. If you like this video, please hit the notification bell if you want more notifications for other videos I put out. Share this video with your friends. Hit the subscribe button, subscribe to the channel. Make a comment in the comment section and let me know what you think, and if there's anything else you want me to cover or any questions you want me to answer. Thanks for joining me, and see you next time.